Hello, I'm David Patterson. This is New Developments in Unsolved Problems on the topic of non-standard analysis. Cardinal numbers are the numbers 1, 2, 3, 4, 5, etc. The ordinal numbers are the numbers 1st, 2nd, 3rd, 4th, 5th, etc. The symbol omega was chosen for ordinal infinity around about the turn of the last century, more than 100 years ago. Now don't be frightened. All the mathematics you need here for parts 1 to 7 were taught in high school. For part 8 you might need first year university mathematics as well, and for part 9, unless you've had a look at the previous 8 parts, first year university is about the mathematics that you'll need here. In non-standard analysis, infinitesimals exist. So, for instance, dy dx equals infinitesimal dy divided by infinitesimal dx. There are 4 routes to non-standard analysis. These are the hyperreals, the transfer principle, Hahn series, and surreal numbers. Some consequences of non-standard analysis include that infinity divided by infinity equals 1, which allows infinity to be used in quantum renormalization. Infinity is not equal to infinity plus 1, and infinity times 0 is always equal to 0. The innovation in this set of originally 8 parts is in part 3, the use of a new limit. I hypothesize that for every sequence it is the sum of a smooth part and a pure fluctuation, and we can take the limit to be the smooth part and ignore the fluctuation. One consequence of this innovation is that there's no such thing as divergence anymore. Every sequence on the reals has a unique limit on the hyperreal numbers. The example I've got here was discussed by Leibniz back in the year 1673, and that was the answer he got. Advantages of this approach are that sequences of real numbers converge, paradoxes involving infinity are resolved, and all orders of magnitude used in physics and computer science are incorporated into the theory. They're not incorporated in standard analysis. In standard analysis, there is a well-known proof that infinity minus 1 equals infinity. That leads directly to the conclusion that there exists a smallest infinite number and that infinitesimal numbers don't exist. Infinity omega is defined as a set of finite natural numbers. Omega minus 1 is infinite and cannot be greater than omega. Assume that omega minus 1 is less than omega, then omega minus 1 must be a member of that set. This is impossible because every member of that set is finite, so omega minus 1 must equal omega. On the surreal numbers, there must exist a number that is larger than all finite natural numbers and smaller than omega, and we call this number omega minus 1, which is less than omega. With the transfer principle, we can omega is defined as the set 1, 2, 3 up to omega minus 1. For surreal numbers, omega is defined as the successor of that set. There has to exist a number that is larger than all finite natural numbers and smaller than omega. Call this number omega minus 1. With the transfer principle, omega is defined as the set 1, 2, 3, 4 up to omega minus 1. On the hyperreal numbers, omega minus 1 is defined as a sequence 0, 1, 2, 3, etc. This is not the same as omega because numbers are not shift invariant. If numbers were shift invariant, then 1 equals 2, which is wrong. Hahn series for omega minus 1 is not the same as the Hahn series for omega. So omega minus 1 is not equal to omega. A few things are still obscure. I haven't defined what I mean by smooth. It's not the normal definition. Does every sequence converge to a unique limit? Integration using Riemann sums doesn't work anymore. How do we handle 1 over 0? And can an equivalence class reduce non-standard analysis to classical analysis? A fluctuating function may be a periodic function, a random function, or a chaotic function. But I stopped short of defining what a smooth function is because I don't have an adequate definition. To illustrate the problems of defining what I mean by smooth, consider this function. The function has derivatives of all orders and all derivatives are non-negative, but it isn't smooth. The definition of smooth is simple enough on the trans series and the Hardy-L field. But there are a whole heap of smooth functions that are not part of transfer series and the Hardy-L field, and they cause problems. We need to define a half exponential function in a way that admits only a single smooth solution, ideally an infinite limit or an integral. A normal definition is the function of x equals e to the x does not suffice. It can be found using a Taylor series, but because there are multiple solutions, does every sequence have a unique limit? A function that is useful for making particularly difficult sequences is the absolute value of tan x. This gives a result that doesn't look quasi-periodic, random, or even chaotic. The limit of the absolute value of tan x should go approximately as that sum. This is plotted as a dotted line on the next image. This has a well-defined limit, but is not necessarily exact. Open question is whether it is exact. An elementary use of Riemann sums doesn't work in non-standard analysis because in that formulation the integral from 0 to 2 isn't equal to the integral from 0 to 1 plus the integral from 1 to 2, which is wrong. Lebesgue integration doesn't work either. We can force a Riemann sum to give us the integral from 0 to 2 equals the integral from 0 to 1 plus the integral from 1 to 2. But the result, this method is actually contrary to the spirit of a non-standard analysis. 1 on 0 is not part of non-standard analysis, but it is part of non-Euclidean geometry. Here, 1 divided by 0 is equal to 2 divided by 0 and is the top point of the Riemann sphere. Looking outside non-standard analysis, is there a mathematics in which 1 divided by 0 is not equal to 2 divided by 0? Well, yes there is, and it's interesting, but it's not very useful. You can read the rest by yourself without audio commentary.